Good morning, everyone. My name is Dan Vinay Dumont-Kiedemann. I am an electrical engineer, and I have worked in system integration, both telecom systems and power management, for over 5 decades. Today, I would like to focus on one specific issue in electrification: surge power. Because many systems are designed for peak demand, but they operate at average demand. That mismatch creates inefficiency, oversizing, and unnecessary fuel use. What I will show today is how intelligent surge management can deliver high peak power when needed, while keeping the system efficient and stable. Let's begin with the real challenge. The electrification challenge. In electrification systems, we often design for the worst-case scenario: acceleration, startup, heavy lifting, sudden load spikes. To survive those moments, systems are oversized. Large batteries, large engines, large generators. But most of the time, those systems operate at only a fraction of their capacity. This creates cost, weight, fuel waste, and mechanical stress. So the question is, can we design for average and manage peak intelligently? Why batteries alone face scaling constraints? Surge power is short duration, high demand energy. It may last only seconds, but it can be 5 to 20 times normal load. Traditional systems treat surge as a continuous requirement. That is inefficient. Instead, surge should be treated as a temporary event, something to be buffered and managed. This change in thinking opens new design possibilities. PHIMS hybrid architecture. This slide shows the architecture. At its core, a steady prime mover, a generator, a supercapacitor bank, an intelligent control system. The engine runs at optimal efficiency. The supercapacitor handles surge events. After the surge, the system rebalances and restores energy. This avoids oversizing the engine or generator. It is not about adding complexity. It is about managing energy flow correctly. How it works. When a surge demand occurs, the control system detects it instantly. The supercapacitor releases stored energy. Voltage and frequency remain stable. After the surge passes, the system restores charge gradually. This cycle happens quickly and repeatedly. Supercapacitors allow very fast charge and discharge. This is key. They respond in milliseconds, far faster than batteries. Demonstration results. Let me explain what this demonstration represents. In controlled laboratory testing, we used a 50-watt primary source. The load required approximately 350 watts during startup. Under normal conditions, a 50-watt source would not sustain that transient demand. With PHIMS architecture, the surge is handled by the supercapacitor bank. The primary source continues supplying average power. This is time domain separation of power. Instant response. Supercapacitors respond in milliseconds. When the load engages, the stored energy is released immediately. There is no ramp-up delay and no collapse of the primary source. No batteries. This configuration does not use lithium batteries. Supercapacitors are optimized for high-power, short-duration discharge. That makes them well-suited for transient surge management. Stable operation. The important result is stability. Voltage remains controlled. The primary source is not overloaded. After the transient event, the system rebalances and recharges. Critical clarification, very important. The total energy still follows conservation laws. We are not creating energy. We are managing when and how it is delivered. Performance highlights: up to 20 times surge power. When we say up to 20 times surge power, we are referring specifically to transient peak demand, not continuous output. This is important. Most electrification systems are sized for peak load, even though that peak only occurs for a few seconds. PHIMS separates transient surge from steady-state power. The supercapacitor bank handles the surge. The primary energy source handles the average load. This reduces oversizing of engines, generators, or battery packs. Up to 90% fuel reduction. This reduction depends heavily on duty cycle. If a system traditionally runs oversized and inefficiently at partial load, significant fuel savings are possible. The key is operating the primary source near optimal efficiency rather than ramping for short peaks. This is not magic. It is load management. Fewer moving parts. Because the system is not constantly ramping mechanical components for surge events, mechanical stress is reduced. That translates into longer service life and lower maintenance. In some configurations, traditional components like large battery packs or oversized generators can be reduced or eliminated. High reliability. Supercapacitors have high cycle life. They respond in milliseconds. They do not degrade the way batteries do under high C-rate surge conditions. This improves stability during accelerations, startup, or load shock. The goal is not bigger systems. The goal is smarter energy flow. Application examples. Let me explain where this began. PHIMS was not originally designed for passenger vehicles. It began in underground mining transport. In that environment, vehicles operate under heavy load, confined space, limited ventilation, and high torque demand. Battery life was short. Equipment was oversized. Efficiency was poor. That was the original problem we were trying to solve. The goal was simple: improve surge performance without increasing system size. Generators and industrial systems. From mining transport, the concept naturally extended to generators. Industrial systems frequently experience startup surge, compressors, pumps, conveyors. Instead of oversizing engines or generators for peak events, PHIMS allows surge buffering. This improves efficiency and reduces mechanical stress. EV and hybrid vehicles. In electric and hybrid vehicles, acceleration is a surge event. Most systems are designed around peak acceleration demand. With intelligent surge separation, average system size can be optimized. This reduces cost, weight, and energy waste. Agriculture and utility equipment. Agricultural equipment has highly variable duty cycles. Load spikes occur during tilling, lifting, hydraulic operation. PHIMS architecture helps stabilize performance during those transient peaks. UAV/aerospace. In aerospace and UAV systems, weight and response time are critical. Supercapacitor-based surge handling provides fast power bursts without long-term degradation. This can extend mission capability while maintaining compact system design. Key message of this slide: the architecture is not industry-specific. It addresses a universal problem: transient peak demand. Wherever there is surge, there is opportunity for optimization. This began in one of the harshest operating environments, underground mining, and scaled logically outward. That gives credibility. It shows real origin, engineering evolution, broad applicability. Sustainability impact. Let's briefly look at the sustainability implications of this architecture. These are engineering outcomes, not marketing claims. Lower fuel use. When systems are no longer oversized for peak demand, the primary source operates closer to optimal efficiency. That directly reduces fuel consumption in hybrid and generator configurations. Reduced emissions. Lower fuel consumption naturally reduces emissions. In addition, stabilizing transient load events reduces inefficiencies during ramp-up and surge. Fewer raw materials. Oversizing for peak demand increases copper, steel, lithium, and structural mass. By separating surge from steady-state demand, overall system size can be optimized. That reduces material intensity per unit of work. Long lifecycle components. Supercapacitors have very high cycle life under high power conditions. Reducing mechanical stress also extends component lifespan. Longer lifecycle means fewer replacements and lower lifecycle impact. Sustainability here is not a separate feature. It is the natural result of better energy architecture. Lessons learned. Let me close with a few practical lessons from development and testing. Practical integration matters. We learned quickly that performance alone is not enough. A solution must integrate into existing platforms, existing controllers, existing mechanical systems, existing workflows. If it requires complete redesign, adoption slows dramatically. Architecture must fit reality. Simpler systems are better. Electrification often becomes increasingly complex. More components, more layers, more compensation. But complexity increases cost, maintenance, and failure points. We found that simplifying energy flow, separating surge from steady state, often reduced overall system complexity. Simple architecture improves reliability. Power management is key. The most important insight was this: the challenge in electrification is rarely total energy. It is managing when and how power is delivered. Transient events drive oversizing. Power management, not just power generation, determines system efficiency. Electrification success depends more on architecture than on component size. Economic impact. Reducing fuel consumption lowers operating cost. Reducing mechanical stress lowers maintenance cost. Reducing oversizing lowers capital cost. The system becomes both technically and economically attractive. Engineering decisions always affect economics. This is an engineering-first improvement with financial benefit. The PHIMS architecture is covered by granted intellectual property, but today I am focusing on the engineering principles behind surge management. Electrification continues to evolve, but surge power remains a fundamental design challenge. If we manage surge intelligently instead of oversizing hardware, we unlock efficiency. The future of electrification is not only more batteries, it is smarter energy management. Thank you. I look forward to your questions.